there, you made it to the very last section of the last chapter. Awesome job. This is the lecture video for Chapter 9, Section 3. In this section, we're going to be doing a little of everything. We talk about deviations, normal distributions, equations of a line, critical values, confidence intervals, and regression lines. There will be some serious calculator work and some lengthy formulas, so make sure you take good notation and calculator notes this time. Have them in a good place for the final. We're nearly there. Let's get started. Welcome to the lecture video for Chapter 9, Section 3, Measures of Regression and Prediction Intervals. Today we're going to learn about the three types of variation that exist about the regression line, how to find and interpret R squared, the coefficient of determination, how to find the standard error of the estimate and use it to interpret the error that is existing in the regression line. Then we're also going to talk about prediction intervals for values of y given a value of x, how to construct them and interpret them. Let's begin. You might recall back in Chapter 2, we talked about deviation with one variable data sets, being the difference between the entry x and the mean. So we said the deviation was x minus mu. Now how might we define deviation in the situation we're talking about now in Chapter 9 with a data set that involves two variables? Well, the total deviation about a regression line is actually broken down into two parts, what we call the explained deviation and the unexplained deviation. Now, just so we're clear on what these different parts mean, y sub I is referring to the observed y value. These are the second coordinates of the ordered pairs that create the scatter plot. Y bar is the mean of the y values, and remember x bar comma y bar is a point that is always on the regression line. And y hat is referring to the response variable that comes from plugging an x value into the regression equation. So y hat is what we're calling the predicted values. So in terms of our picture here is a point x comma y that's coming from the data set. So the second coordinate of that ordered pair is an observed y value. We have this point on the regression line where the second coordinate is a y hat value because it's a predicted y value because it's a response variable that's coming from the regression equation. Then we have the point x bar y bar for which the regression equation always goes through. So we have this third point here, x sub I comma y bar, where its second coordinate is the mean of the y values. Now the distance between these 3 points is what we're calling the total deviation, the distance from the observed y value to the value of y bar. It is broken down into the explained deviation, which is the distance from the y hat or predicted y values to y bar, or the mean of the y values, to what is called the unexplained deviation, which is the distance from the observed y values to y hat, or the predicted y values. Together, these three values help us define the three types of variation that exist about a regression line. The total variation is the sum of the squares of the differences between the y value of each ordered pair and the mean of y. So it's the sum of the differences of two of those types of y values we just saw squared, and the two specifically are the observed values and the mean values. The explained variation is the sum of the squares of the difference between each predicted y value and the mean of y. So this is very similar to the previous one. It's a sum of the differences of two of those types of y values squared, and the two specifically are y hat or predicted y values and mean values. The unexplained variation is the same thing, the sum of the squares of the differences between the y value of each ordered pair and each corresponding predicted y value. The sum of the differences of two of the y values squared, and the two specifically are the observed y value and the predicted y values. The unexplained variation could be due to sampling error, lurking variables, or coincidence. These are some of the factors that could result in some unexplained variation that exists in some of the observed data points. Interestingly, the sum of the explained and unexplained variations is equal to the total variation, which kind of makes sense if you think about it. That's what's happening in the picture. The explained and unexplained are different parts of the total variation. Here is a ratio that is important. It's the relationship between the explained variation and the total variation, and it's denoted by lowercase r squared, which is the square of the correlation coefficient, which we talked about before, and it's called the coefficient of determination. It is literally the correlation coefficient times itself. So for example, if we have r equals 0.88 and we find that the coefficient of determination is that number squared, or 0.7744, what does that mean exactly? What are we saying? Well, it means that 77.44% of the variation in y can be explained by the relationship between x and y, between the two variables. The remaining 22.56% is due to other factors, such as sampling error, lurking variables, or other things like we talked about a moment ago. Remember when we were dealing with x bar that we said it was a point estimate for mu? Well, when dealing with a two-variable dataset, when given an x value, the predicted y value, or y hat, is a point estimate. So just like we constructed intervals for mu using x bar, we can construct intervals about y hat for a given value of x. We use what's called the standard error of estimate. It is the standard deviation of the observed y hat values about the predicted y values for a given x value. It is given by this formula, where n is the number of ordered pairs in the dataset, or the number of data points. We read this S sub e to denote the standard error of estimate equals the square root of the sum of y sub I minus y hat, which should look familiar because it's the same as the deviation used in unexplained variation, the sum of those squared values divided by n minus 2. Now, why are we calculating this value? The closer S sub e is to 0, meaning the smaller S sub e is, that means the closer my observed y values are to the regression line. This is a measure of error. How far away or how spread out are my observed y values in comparison to my predicted y values, my y values that are on the regression line? Let's do a quick example solving for the standard error of estimate using the gross domestic product and CO2 emissions data from a previous section. You might remember that the regression line for section 2 for this data set was y hat equals 187.660x plus 44.663. Using this regression line, can we find the standard error of estimate? Let's think about what we would need in order to find the standard error of estimate. If we were to do this by hand, there's a clue right there, we're not going to be doing this by hand. We would have to use our observed y values and also come up with their associated predicted values. In other words, plug in all of the x-coordinates to get the y hat values for each one of our observed y values. Then we would have to find this difference, square all of those differences, sum them all, divide by n minus 2, and take the square root. Yeah, not a pretty picture. Let's not do that. Here's how we'll be doing this using the calculator. Okay, this is a little bit of a process, so if you need to pause this to take notes, feel free to do that. We first need to create a list of the y hat values. Since the y hat values are the predicted values for given x values, we can use the x values we've already entered from the previous section. I have my data in L3 and L4, so that's how I'm referring to my initial x and y data. Yours may be in a different place, just make sure you keep it straight for yourself. So we can use the regression equation, which hopefully you also still have in the y equals line of your calculator. If you do not have that, put that into your y equals line first. All you have to do is press y equals button and type this in. So to create the y hat values, we press the stat button, then enter, then highlight the heading of the next blank list you have. Mine was L5, so I arrowed over and up to highlight L5, then press the vars button, arrow over to y vars, or y variables, press enter to choose one function, and then press enter to choose one y1. That's y variables. Then type open parentheses, then the second button, and the number of the list that has your x values. Then close parentheses. Now your y hat values are stored in this new list. Remember that list's number. Now go to the main screen by pressing second button and mode. Now you're going to do some of the calculation using the list names as variables. Type open parentheses, then second, then the number of the list that has the initial y or y sub I values, then the minus sign, then second, and the number of the list of the y hat values that you just created. Then close parentheses, then the x squared button. Now you want to store this value. Don't press enter yet. You want to store this value, so press the STO button. It's just above your on button. It has a little arrow. Then the second button and the number of the next blank list to store these values to. So whatever the next L number is that you don't have anything in yet. Now we're going to come up with the sum of this new list by running the one variable statistics function. So we do that by pressing the stat button, then arrow over to calc, press enter, and change the list to the newest list by pressing second, then the new number, then press enter. Now you have the numerator for the fraction within the square root of the equation. So you want to note that number. You should have come up with 181,608.0754. When we put this in with our value of n at 10 and take the square root, we get standard error of estimate of 150.669. We can interpret this as the standard error of estimate of the carbon dioxide emissions for a specific gross domestic product is about 150.669 million metric tons. What this means is that it's deviating 150 million metric tons for a specific gross domestic product. Okay, if you didn't get all of that calculator instruction, you can rewind and pause if you need to. I'm going to go over this in words and symbols, but this is one case where I think you can probably do this quicker with the calculator with some simpler notes than what they describe here. They're basically describing what we just did, but breaking it down into table format and doing each part a step at a time. We did it more in a step-as-you-go method. I'm including these instructions in case there are some of you who this will work better for. If the way we just did it and the notes you got from that work well for you, stick to that and don't worry about these next few slides. If you had trouble following that, maybe this will help you. So here it goes. First, make a table that includes the following column headings: X sub I, or observed X values, Y sub I, or observed Y values, Y hat sub I values, or predicted Y values, the differences between observed values, or Y sub I, and predicted Y, or Y hat values, and the differences squared. Those are all columns that you should have in this table. Then use the regression equation to calculate the predicted Y values, or the Y hat values. Then calculate the sum of the squares of the differences between each observed Y value and corresponding predicted Y value. This actually is assuming you've filled in all of your columns, because if you look above, you have columns for finding the differences and the differences squared. So this step is just finding the sum of that last column. Then finding the standard error of estimate, which means plugging in your n value and the last sum into the square root and calculating. Here's what that table would look like. Please use whichever method makes the most sense to you. If you can keep track better this way and it helps you, go for it. And as we noted before, your final result is the same as the unexplained variation total. So all this leads to a discussion about prediction intervals. Remember how we did confidence intervals? This is very similar to that. We say that two variables have a bivariate normal distribution when for any fixed value of x, the corresponding values of y are normally distributed. Remember that sample data supplies us with a scatter plot through which we attempt to draw a linear model, the regression line. So you can imagine that in this picture, I've got a scatter plot with all kinds of points recorded, and the dotted line is our regression line, or our line of best fit. So for one value, say x sub 2, we have this observed y value, y sub I. But we also have this predicted y value, or y hat, that lies on the regression line because it is predicted using the regression equation. And somewhere along this interval, there exists the true y value. So we're saying that any two variables have this bivariate normal distribution if we can say that for any fixed value of x, the corresponding values of y are normally distributed, and that works for every x value. Similar to what we've done in the past, we can construct a prediction interval for the true value of y. Given a linear regression equation y hat equals mx plus b and a specific value of the independent variable x naught, the C prediction interval for y is the point estimate y hat minus an error as our lower bound, and y hat plus an error to create our upper bound, where this value of the error is defined using a critical t value, the standard error of estimate, times the square root of 1 plus 1 over n plus n times x naught minus x bar squared over n times the sum of the squared x value times the sum of x quantity squared. Now remember, y hat is the point estimate, E is our margin of error, C is the level of confidence. It's also the probability that the prediction interval contains the true y value. And again, as usual, this all assumes that the estimation process is repeated a large number of times. Okay, let's go through one. Construct a 90% prediction interval for the CO2 emissions when the gross domestic product is $2.8 trillion. What can you conclude? Because n equals 10, there are n minus 2 or 8 degrees of freedom. So let's hold on to that number for later. Next, we have our regression equation from before. Y hat equals 187.660x plus 44.663. And x for this situation equals 2.8. We can find the point estimate, or y hat, by plugging the specific x value into the equation. We get 570.111. No matter which way we do the next part, we need to distill some of the information we have. They asked us to construct a 90% prediction interval. This means 0.10 to split into 0.05 confidence intervals. So the area we work with is 0.05. Also, we need to remember that degrees of freedom is 8. Now we can use the table 5 from Appendix B, or use the inverse t function on your calculator. Use the second and vars button to get there. It's option 4, and we use 0.05 for the area. Either way, our critical point is plus and minus 1.86. Other information we need that we've already found is the S sub E, which was 150.669. Earlier in the process, we found the sums of the x's to be 25.7, and the sums of the x's squared to be 82.81. Also, the x bar value is 2.57. Using these values, we plug into this scary looking formula. We have 1.860 times 150.669 multiplied by the square root of all the rest of this, 1 plus 1/10, plus the ratio 10 times the square of the difference, 2.8 minus 2.57 divided by 10 times 82.81 minus the square of 25.7. Okay, we should get 294.344. So that is our error. Now we have to subtract that and add that to our y hat value to get our prediction interval. So our y hat value is 570.111, and our error was 294.344. So our prediction interval is constructed like this from both sides, subtracted from and added to the y hat. 570.111 minus 294.344 is 275.767, and that number plus 294.344 is 864.455. So we have our prediction interval has a lower bound of 275.767 and an upper bound of 864.455. And you can state it this way. You can be 90% confident that when the gross domestic product is $2.8 trillion, the carbon dioxide emissions will be between 275.767 and 864.455 million metric tons. Again, here's how we did that in words and symbols if you need that. First, identify the number of ordered pairs in the data set, n, and the degrees of freedom. And remember, it's n minus 2. Next, use the regression equation and the given x value to find the point estimate y hat. After that, find the critical value t sub c that corresponds to the given level of confidence c. Use Table 5 in Appendix B or the inverse t function on your calculator to do this. Next, find the standard error of estimate S sub e. Then find the margin of error. This involves using some of the info you found at earlier stages. Finally, find the left and right endpoints and form the prediction interval. Now that was summed up really briefly. You saw how much work we did to get through those steps, but if it will help you remember what to do, definitely take down these notes. Okay, that is it for this section, for this chapter, and for this semester. You did it. Great job. Make sure you understand how to do the calculator functions and formulas we tackled in this one. There were some beasts in there. Make sure you have good notes so you know where to find them come final time. Please feel free to come to me with any questions. Good luck. So long.